you know that our planets does not orbit in a perfect circle? Then how do they orbit? Buckle up and listen until end of this video to know more about Kepler's law of planetary motion. Let's get into our video. In 1609, the German astronomer Johannes Kepler published his book called Astronomia Nova, outlining his discoveries, which are now called as Kepler's law. First two laws of planetary motion. In this book, he explained how all the planets in the solar system follow certain laws to move around the sun. Well, before we jump into the laws, there are a few basic things you need to know about a shape called ellipse. That has two focus points called foci, which is a plural of focus. The foci is always lie on the major or longest axis, spaced equally on each side of the center. But why are we learning about ellipses? That's because Kepler's first law states that all the planets revolve around the sun in elliptical orbits, having the sun at one of the foci. In other words, the path these planets following during a revolution is always elliptical shape, with the sun located at one of the foci points of the major axis. Why are we learning about ellipses? That's because Kepler's first law states that all the planets revolve around the sun in elliptical orbits, having the sun at one of the foci. In other words, the path these planets follow during a revolution is always elliptical shape, with the sun located at one of the foci points of the major axis. Now, let's witness a simulation for Kepler's first law. Here we can see or witness that all planets move in elliptical orbits with the sun at one focus. Isn't it easy, my dear students? Now let us see the second law. Imagine a line appearing from the sun and joining a planet. This line is called the radius vector. Now let's assume this planet moves from position P1 to position P2 in a certain interval of time. Now, along with the position of the planet, the position of the radius vector has also changed, and its movement has covered a certain area as well, which we will call A1. Now, let's move this planet to the opposite side, where it travels from position P3 to position P4 in the same amount of time, denoted by the alphabet T. And the area covered by the radius vector is denoted by A2. And yes, you will be surprised to know, according to Kepler's second law, area 1 will be equal to area 2. And the second law states the radius vector drawn from the sun to the planet sweeps out equal areas in equal interval of time. Though Kepler was able to see the smooth ride of the planets, his personal life was going through many ups and downs. That's why it took him almost a decade to publish his next book called Harmonious Month, in which he explained the third law. The minor axis and the major axis, whose half distance is called the major axis. Now, as we know, a planet denoted by the alphabet P takes one revolution around the sun in T time, also called the time period. In simple words, it explains how long a planet takes to finish one revolution depending on its position from the sun. Meaning, as a planet's distance from the sun increases, the time they took to orbit the sun increases rapidly. And no matter what, for every planet, the square of its time period will always be the same, as the cube of its length of its semi-major axis. And that's it. Easy marks for you right there. Let us recap the Kepler's first, second and third law. Kepler's first law states that all the planets revolve around the Sun in elliptical orbits having the Sun at one of the foci. And Kepler's second law states the radius vector drawn from the Sun to the planet sweeps out equal areas in equal intervals of time. Kepler's third law states that the square of the time period of revolution of a planet around the Sun in an elliptical orbit is directly proportional to the cube of its semi-major axis. As we wrap up our cosmic exploration today, we have journeyed through the groundbreaking laws of Kepler. I hope this journey into Kepler's law has sparked your curiosity about the wonders of space. Next time, keep looking up and stay curious.